Hey guys, here's a video on composite functions. So this is actually a topic in MHF for you. So if you've already taken advanced functions, you may have seen this. If your teacher covered composite functions, it's probably at the end of the course. It would be one of the last things you learn in advanced functions. So if you're currently taking advanced functions, it's likely that you've never heard of composite functions. But they're kind of important to know for our final derivative rule in A3, which is the chain rule. So composite functions are just functions that are composed of other functions. So let's just say, let's do an example. Like let's say you had two different functions. Like let's say you had f of x is equal to x cubed plus 1. So there's a cubic function. Okay, then let's say you have another function. Let's call it g of x. And we'll make it a rational function, and we'll say it's 1 over x minus 2. So you have two separate functions there. So using composite functions, you can combine those into one function, or into a composite function, which is what the chain rule is going to be doing. So what that would look like is I could make up a function composed of both of these functions. For example, I could say, I could determine what g of f of x is. So that's what it would look like. So it's pronounced like g of f of x, or g of f at x. So what it is like, you know how normally we would write, g of x, or when we did limits, sometimes we'd be g of x plus h, or something like that. Like this is like your input. It's your x value. That's what goes in your equation. So g of x is 1 over x minus 2. Well, if you now put a function in that input, that basically means that anywhere you see an x in g of x is actually going to be replaced by the function f of x. It's going to actually take the place of x. So kind of crazy, but here's what it would look like. So you would take your g of x, so 1 over, but instead of x minus 2, in that x spot, you would be putting your f of x. So x cubed plus 1 minus 2. So you can see that you have your g of x function. That's like kind of your outer function, 1 over x minus 2. But then for our input, f of x, we actually replaced the x term in g of x with our f of x function. So it's kind of a function within a function. And then I could totally simplify that further to be 1 over x cubed minus 1. So that's what a composite function is. And I can do it the other way too. So using these same two functions, like let's say I want to find out what's f of g of x. So now f is like my outside function and g is my inner function. So I start with f of x. So it's like, I'll just write it, x cubed plus 1. But now I actually don't want that x to be there. I want to replace that x with g of x. So instead of x cubed, I'm going to have 1 over x minus 2 cubed plus 1. So that's how you do like f of g of x. It's still your kind of your original function, x cubed plus 1, but instead of the x, you're putting in a g of x. Let's just try one more, just in case you're like, what? Okay, let's say you had h of x is equal to square root 1 minus x squared. And then let's say you had f of x is equal to, x squared plus 3x. Let's do a tricky one. Okay, so now you've got two functions. You've got a quadratic and a radical function. So let's just say we were like, ooh, what's h of f of x equal to? So there's a composite function. So, okay, we take h of x. So we got square root of 1 minus x squared. But instead of that x value, you're going to replace that x value with f of x. And f of x is x squared plus 3. So it's going to become instead of that x squared value, it's becoming x squared plus 3x squared. So you kind of keep it exactly as it is, like 1 minus something squared. But instead of that x value, you just put in brackets whatever the inner function is. So whatever f of x is goes in the x spot. Okay, and let's say we wanted to do the opposite. Let's say we wanted to find f of h of x. Okay, so f is our outer function now. So our outer function is x squared plus 3x. But remember, our inner function is h of x. So now, instead of these x's here, we're going to get rid of those x's. And we're replacing them with this as our input. So, got to get rid of that x. And instead, in its place, there's going to be a square root 1 minus x squared. I should have obviously left myself more space. It's really tiny. So I'm replacing that x with a 1 minus x squared, since that's what it was like in f of x. So this is like our new x squared term, plus 3x. So I'll just get rid of that x, and in the x spot, I'm putting the h of x. So I don't know if you need to keep that in brackets, probably not, since it's under a radical sign, but whatever. So there you go. So that would be f of h of x. So these are called composite functions, and they're going to be super useful when you learn the chain rule, which is coming very soon. Chain rule, like most important derivative rule in calculus. Because what we haven't been able to do yet is figure out how to find the derivative of, for example, using the product rule. Say we had like x plus 1 cubed times 2x, actually, times like 3x minus 1 square rooted. So we want to use the product rule, but it turns out we have functions within functions here. So like here we have a cubic function, but inside it's a linear function. So, yeah, I'm not going to teach the chain rule right now, but we're going to need it when we try to do the derivatives of composite functions. So hopefully this kind of made sense to you. Consult your advanced functions textbook. It should be in there somewhere. Probably near the end, I guess. Rates of change after that. Composite functions are called. All right, guys. See you later.